What if in 1942 the Allies built an aircraft carrier? Not from steel, but from ice and wood pulp. Not a small escort ship, but a floating fortress the size of a battleship. A base at sea to house planes, fuel, and men. A ship so huge nothing could sink it. That was the bold promise behind Project Habakkuk. Its creator was Geoffrey Pike, a Briton whose background was journalism and education, not shipyards or naval architecture. Yet when war threatened Britain's supply lines, Pike proposed an idea so wild it almost worked. The plan was to build a floating iceberg ship made of a material called pykrete, a mix of ice and wood pulp. Use cheap, abundant resources instead of precious steel and aluminum. Give the Allies a mobile, unsinkable base in the Atlantic where none existed. If it worked, the war at sea might have changed forever. By the early 1940s, the Atlantic Ocean was the lifeline of the Allied war effort. Supplies, troops, fuel, even food flowed from the Americas and Empire to Britain and Russia. German submarines prowled those waters targeting convoys in the mid-Atlantic, far beyond range of land-based air cover. Every lost ship meant fewer guns, fewer men, fewer chances. The U-boat threat was strangling supply lines. Conventional warships couldn't effectively patrol every dangerous mile, and steel and aluminum, materials needed for planes, tanks, ships, were stretched thin. Building escort carriers or full fleet carriers wouldn't cover the gap quickly enough. That's when Pike pitched his idea, the ice carrier. His argument was that water is everywhere. Freezing water costs almost nothing to produce compared to steel, and a hull made of pykrete might be strong, cheap, and enormous. It wasn't a fantasy born of comfort. It was an engineering answer to logistical desperation. If the Allies could plant an airfield in the middle of the Atlantic, one that enemy torpedoes couldn't easily sink, they could protect convoys, tip the sea war, and keep the supply lines alive. That need made the wild idea of an iceberg carrier suddenly serious and dangerous enough to almost get built. The man behind the idea wasn't a shipbuilder. Geoffrey Pike was what the British establishment called an eccentric intellectual, though that doesn't do him justice. He spoke multiple languages, escaped from a German internment camp in World War I, and had spent the interwar years pitching radical plans for education, fuel, and infrastructure. His ideas were so unconventional that no one could tell whether he was a genius or a liability. In 1942, Pike joined Combined Operations Headquarters, the British think tank tasked with finding unorthodox solutions to strategic problems. This unit, led by Lord Louis Mountbatten, didn't care where ideas came from, only if they could win battles faster than the Axis. Pike's proposal was simple. Don't build ships out of scarce metal. Build them out of pykrete, water frozen together with wood pulp. The wood fibers strengthened the ice, slowed melting, and made the resulting material far tougher than plain ice. With refrigeration, it could remain solid even in moderate climates. He named the material after himself, pykrete, and he needed someone credible to prove it wasn't a joke. That someone turned out to be Max Perutz, an Austrian-born scientist then working in Britain. Perutz was a serious researcher, not a dreamer, and his endorsement gave the idea weight. He conducted freezing tests, measured strength, and reported that a block of pykrete could resist bullets better than many metals at similar thickness. This was exactly the kind of data that Mountbatten loved. He demonstrated its strength for senior officials by firing a pistol at a block of pykrete which didn't shatter. The demonstration wasn't theatrics, it was proof that the material could take hits. More tests followed. Engineers chilled prototype samples, measured stress loads, tested melting rates, and tried shaping panels into hull-like slabs. Pykrete behaved strangely, but promising enough to encourage the next step, a full floating prototype. If this material could withstand temperature, pressure, and impact, it might support runways, fuel tanks, and personnel quarters in the middle of the Atlantic Ocean. The Allies weren't just evaluating an idea, they were on the edge of inventing a new class of ship. Once pykrete proved viable in the lab, engineers moved from experiments to blueprints. The idea wasn't a small platform, it was a mobile airbase in the Atlantic, a ship roughly 2,000 feet long, 300 feet wide, and a hull up to 40 feet thick. This would make it far larger than any warship afloat. It needed hangars for hundreds of aircraft, workshops, fuel tanks, and quarters for thousands of men. Its walls, made of pykrete, 86% frozen water, 14% wood pulp, would be tougher than regular ice and theoretically resistant to torpedoes. Some planners genuinely believed German submarines would bounce off it. Then came the price. Early proposals sold the concept as cheap. Jeffrey Pike pitched the structure as a mountain of frozen water, not a steel ship. Steel was scarce. Water wasn't. His promise hooked decision-makers. But once naval architects crunched real numbers, refrigeration plants, power generation, insulation, timber pulp production, labor, towing infrastructure, the estimate grew. Documents circulated inside combined operations placed projected costs at over £10 million, and that didn't include long-term cooling and maintenance. Other estimates later ballooned far beyond that once scaling calculations were done. In the middle of a total war, £10 million for a ship made of ice was no joke. It was more than entire armored divisions cost. Yet, remarkably, no one canceled it. Not yet. The British wartime machine had reached the point where building a floating glacier seemed like a practical option. Building a floating fortress out of ice required more than blueprints. It needed proof. For that, the Allies chose a remote mountain lake, Patricia Lake in Jasper National Park in Canada. The frozen winters, rail access nearby, and relative secrecy made it ideal. Starting early 1943, a small team, 15 men, many of them conscientious objectors assigned to alternative service, set to work building a 1:50 scale model of the ice ship on the frozen lake. The prototype was roughly 60 feet long by 30 feet wide, enough to test flotation, insulation, and the basic viability of pykrete at scale. It weighed about 1,000 tons. They laid down wooden support structures on the lake ice, installed refrigeration pipes and a modest cooling system, then gradually built up the ice hull around it. For months it froze, held shape, floated, and survived lake conditions that varied sharply with spring sun and thaw cycles. Scientists, including Max Perutz, the same researcher who had validated pykrete in lab conditions, observed the prototype. Early tests showed pykrete could sustain structural stress and was significantly tougher than plain ice, more resistant to cracking, melting slowly, and capable of withstanding small arms fire or blows that would shatter normal ice. That success sparked serious enthusiasm among senior Allied leadership. For a time, the iceberg carrier wasn't dismissed as a crazy idea. It looked like a plausible fallback if structural and logistic challenges could be overcome. But the scale model didn't settle the real problems. The refrigeration plant was rudimentary and only sufficient for a small hull. Scaling it for a full-size carrier would require a mobile power station. Cold storage alone meant steel, piping, insulation, exactly the scarce materials the project was meant to circumvent. And repairs at sea would be tricky once battle damage melted parts of the hull. Still, for a few months in 1943, Allied engineers had laughed at the odds and simultaneously believed they might just beat them. The Patricia Lake prototype proved that pykrete held together, but scaling it up from a barge to a 2,000-foot warship introduced problems that no one had fully grasped. First, heat. Engines, men, ammunition, aircraft maintenance, everything on a warship produces heat. Ice hates heat. A vessel the size of Habakkuk needed not fans, but an industrial cooling plant running day and night to stop the hull from softening, sagging, or cracking. Engineers calculated it would need miles of refrigeration coils powered by huge compressors. That required steel, fuel, and more electricity than many British towns consumed. Second, weight and stress. A hull half a kilometer long made of picrete was stable at rest, but the ocean is not calm. Waves, storms, and torpedoes exert force. Naval architects realized the hull would flex like a glacier, too slowly to break immediately, but enough to shear internal structures over time. To prevent this, they needed a steel skeleton inside the ice, exactly the material the project was supposed to avoid. Third, pulp supply. The wood pulp requirement exceeded available Canadian forestry capacity earmarked for other wartime uses. Converting whole forests into a single ship of frozen sawdust was no longer a clever hack, it was a strategic drain. Fourth, propulsion. Someone had to move this thing. Early proposals called for dozens of electric motors mounted along the hull, but where would the electricity come from? Power plants strong enough to move millions of tons of frozen ship turned the floating iceberg into a floating city with its own power grid. A terrifying realization dawned on planners. To solve the U-boat threat, they were building a problem larger than the U-boat threat. Each solution required new machinery, new parts, new workers, and new shipping lanes. The result was the opposite of the original pitch. Habakkuk was supposed to be cheap because it was ice. It was becoming expensive because everything that made it usable wasn't. And while engineers wrestled with physics, the war was changing. Escort carriers were rolling off American shipyards. Long-range aircraft like the B-24 Liberator were finally closing the Atlantic air gap. Radar and code breaking were throttling U-boat effectiveness. The Admiralty concluded that a full-sized Habakkuk would not be ready before the end of the war. The U-boat threat was declining and resources were needed for equipment that actually existed. The decision was made quietly. Stop development and shut down the test program. The prototype on Patricia Lake was abandoned. When the refrigeration was turned off, the structure weakened and eventually sank into the lake, where parts of it remain submerged today. A plaque marks the site, but the prototype itself never resurfaced. Max Perutz returned to scientific work and later won a Nobel Prize for his research into the structure of hemoglobin. Jeffrey Pike did not fare as well. After losing support for his ideas and becoming increasingly isolated, he took his own life in 1948. Project Habakkuk was the closest he ever came to seeing one of his concepts turned into reality.